when you're naming a geometry, the geometry name, for example, when we looked at square planar, we're only actually naming where the bonds are, where actual atoms are. The name doesn't really depend on the lone pairs. And also when you draw a geometry, you don't always have to draw the lone pairs in, but you have to remember that the lone pairs are very much affecting the angles within your molecule and also the actual shape. So for example, let's start talking about different types that have lone pairs in it. First of all, thinking about AX2E. So we have one lone pair, and the geometry here is bent. And I want you, thinking about lone pair repulsion, to tell us what you think the angle between these bonds are going to be. And let's take 10 seconds on that. Okay, good, 75%. That's not bad. Let's think about why. It's going to be less than 120 degrees because we know that normally in a trigonal planar situation, we have an angle of 120 degrees. And since lone pairs are going to cause more repulsion, we're actually pushing down these two bonds here closer together. So what we end up seeing is that they're going to be less than 120 degrees. And it depends on the actual molecule what the exact angles are going to be. So you never have to learn the exact angles in terms of lone pair electrons. You just need to be able to tell us that the bond angle is going to be less than 120 degrees. So let's look at another example here, AX3 with one lone pair, E. This is called trigonal pyramidal. Again, you have trigonal because there's 3 atoms bonded to the central atom, and this looks like a pyramid here.
So what would the angle of this be? I think I heard it.
I think so too. All right, less than 109.5. Let's take another example, AX2E2. This is also bent. So again, tell us what the geometry, or we told you the geometry, tell us what the bond angle is going to be between these bonds. So let's take 10 seconds on this. Oops. Let's repull F4. So 10 seconds again. Not going to happen. Just go to the... All right, think about 10 seconds. Darcy, in 10 seconds, we'll hit the next slide. This is not her fault. It's with the program. So. All right, I think that's about. OK, so it's less than 109.5 degrees now. So some of you wrote that it was less than 120 degrees. And we can think about, if we switch back to the class notes, the difference here. So even though, so this is now going to be less than 109.5. If we looked at the case where we had bent in the first case, that started with 120, and one of those bonds was replaced with a lone pair. But now we have 2 lone pairs here. So now what we're going to see is that the 2 bents are not, in fact, equal. The bent where you started with a tetrahedral shape is actually going to be less than 109.5. And Professor Drennan can maybe show us that with the models here.
It's a little hard to see, actually, between the 2. But I think it's easier to see on this. That if you consider the sort of starting place for the 2, if you look at the bottom set and you put orbitals, so it depends on your starting geometry. You can be bent if you take off these bonds on the top, but it depends on what the starting geometries were. And so you will go with your starting geometry. If it was 109.5, it'll be less than that. If it's 120, then it's less than that.